Hello, how are you doing today? I hope it's awesome. I hope it's a light day for you. What do you mean, powers? Well, we're talking about light today. Okay, we're going to talk about electrons and light. And this is basically about the modern theory of the atom. And one of my favorite topics that it's associated with is light. Okay, so today we're going to get into how the electrons and light are associated with each other. So you're going to love this, okay? It's going to be awesome. I think you're going to like it a lot. So, modern atomic theory. Our objectives today, I want you to describe the experimental evidence and the electrons in the Bohr model of the atom. We're going to talk about valence electrons. I want you to be able to identify and be able to count out the number of valence electrons. And I want you to be able to describe the evidence that has kind of brought us to this idea that the modern atom is something that is associated with electrons and light. Okay, so it's going to be pretty cool. We're going to see how the shape of the this new model, okay, the shape of the atom is way different. So how do fireworks work? Okay, the modern model of the atom is going to help us to explain fireworks. And it's going to be kind of fun at the end. We'll kind of wrap it up and bring it back to fireworks a little bit. But I wanted to talk about Niels Bohr. Niels Bohr is the guy that basically helped us understand that every atom, okay, has a characteristic fingerprint of light. So if we look at a particular element, it's going to have a particular fingerprint. So if we look at hydrogen here, we can see this red line here, we can see a blue line, and then a violet line. It's actually got 4 lines. I can't see where the other one is right now. But hydrogen basically has 4 lines. We'll see some of them a little bit later. What happens is if electrons get excited, they jump up energy levels, then they fall back down, and they give off this characteristic fingerprint of light. And every atom has a unique fingerprint. Okay, we'll talk more about that later. So for instance, this is neon. You saw that hydrogen just had 4 little lines, right? Neon's got a ton of little lines, mostly all these little red ones, some yellow and orange, and then some greens over here. And, you know, neon signs. You think about what a neon sign is. What we do is we excite those electrons, we get them energized, they jump up energy levels. When they fall back down, they give off light. So we get characteristic colors from the way that the electrons get excited and move. Isn't that interesting? All right, so here's Bohr's model of the atom. Basically, he kind of came up with the planetary model of the atom to kind of say, okay, well, the nucleus is kind of like the center, like the sun, and we've got these different orbits around the outside. Those are kind of like the orbits of planets around. Okay, now this model is not the modern model, but it is probably one of the things that kind of stepped us toward the modern model quickest, all right? Because what we started seeing with Bohr's experiment is that hydrogen produced these 4 colors of light, like you saw here a little bit ago, right? And so he realized that electrons could only be in certain energy levels, okay? That they didn't zip back and forth between, but they had to be at particular levels. And electrons that were further from the nucleus had more energy than electrons that were closer to the nucleus. And so that told him a little bit of something too. Okay, so these were 2 different, steps toward helping us understand the modern model. Now, notice that there's a different number of electrons at each of our different energy levels. The first energy level can only hold 2 electrons, second 8, the third 18, and the fourth 32. Okay, now as you go on and higher and higher, you could actually hold more. None of our energy levels actually hold more than 32, but theoretically, if you discovered more and more elements, we might find energy levels that were holding more than 32. Okay, so energy levels are like the rungs of a ladder. Okay, again, you could be on this step of the ladder or that step of the ladder, but you aren't in between, right? You can't be like hovering in between unless you're like, oh, super strong, maybe. But atoms aren't like that. Okay, electrons aren't like that. They can only be on certain levels. And as you get further and further out, those levels are a little bit closer to each other, okay, as you go further. So let's look at what these electrons might look like if we were looking at an atom. Okay, so our nucleus here has got 3 protons. Let's pretend it's got 3 neutrons. We've got 3 positive charges, right? And we can have 2 electrons in the first energy level. We can have 1 electron in the third energy level. We've got to have 3 electrons to balance out our 3 protons, right? Because it's a neutral atom. If we did fluorine, we'd have 9 protons, Okay, so 9 positives. We got 9 neutrons. Remember, those have no charge. And then what do our electrons look like? Well, we'd have 2 at our first energy level. And then 1, 2, 3, 4, 5, 6, 7. We'd have 7 in our second energy level to make a total of 9. That's 9 electrons and 9 positives, 9 negatives, right? Now, if you look at the periodic table, you'll notice that fluorine is number 9, and it's got 9 protons, 9 electrons. But notice the column it's in. It's in group 17, okay, or family 17. Notice something. Here, lithium was in group 1. How many valence electrons does it have? Fluorine is in group 17. How many valence electrons does it have? Interesting, right? If you look at the column of the first 2 and the last 7, you're going to see, or last 8, you're going to see that the number of valence electrons is equal to the group number if you take away that 1, right? So that was group 17, but 17 valence electrons. All right, let's look at chlorine. Now, chlorine has got 17 protons, right? 17 positive charges. It's got, we're just going to pretend like it has 17 neutrons. It actually is 18 for the most common isotope. But then we go on and we look at what are the electrons. So we've got 2 in the first energy level. Now, the second energy level, remember, can only hold a total of 8. There's 4, 5, 6, 7, 8. Now, the third energy level, now I've got 10 electrons so far. Third energy level's got to balance out so that we can only have a balance of 17, right? So I've got to put in 1, 2, 3, 4, 5, 6, 7, done. So now I have 7 valence electrons. Chlorine has got a total of 17 electrons, right? So now we're at 17 electrons there. We were at 9 electrons here. And we were at 3 total electrons there, right? So what group? Well, this one's also in group 17. Guess how many valence electrons we have, right? 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. So you just need to see that the column corresponds to the number of valence electrons. Also notice one thing, that the number of valence electrons is going to characteristically give these atoms some very specific properties of reactivity. Fluorine and chlorine are similar. They're both called halogens. They're both gases when they combine with themselves, fluorine F2 and chlorine Cl2. And they're both poisonous gases. They have some similar characteristics, okay? So the number of valence electrons has a lot to do with the properties of reactivity that those atoms have, okay? All right, so let's look at our valence electrons. So we define them as the electrons that are the outermost energy level of an atom, okay? So whatever the outermost energy level is at that time, that's the valence electron. Okay, that's the number of valence electrons. So if I just have 1 energy level, I can have 2 total electrons, 2 valence electrons. If I get to the second energy level, now I can add 8 more electrons in my second energy level, and so my max number of valence electrons is 8. If I go to the third energy level, I can actually get 18 electrons in my third energy level. And I didn't show you that last circle there on chlorine, but I could have kept popping stuff in. And we didn't, but we could have gotten all the way up to 18. The number of valence electrons, though, is only 8. Look at this. You can only have a max of 8 valence electrons. You notice that. And remember, I said that column number is going to give you an indicator as to whether, how many valence electrons it can have. Notice I go up to column 18. There's no more column beyond that, right? And so 8 is the maximum number of valence electrons you can have. First energy level is only going to have 2, but all the others are going to have 8. Okay? Pretty easy to remember that, right? All right, so let's talk about electron transitions. I've got a term called ground state and excited state. The ground state is that lowest level of an electron. The excited state is what's going to happen when it gets excited, it moves up. Now, there's 2 ways of thinking about the electron moving up. The ground state is, closer to the nucleus, but it's also vibrating slower, okay? Electrons vibrate with wave-like properties. And if you excite it, it's going to speed up its vibration as well. So not only does it go higher, it speeds up its vibration. It's an excited state. It's a greater energy state. Okay, now why does it get excited? It absorbs a photon. photon is light, okay? There's light hitting me right now from this ring light, right? Those photons are striking my body. They're hitting all my electrons, and the reason you can see me is because light is bouncing off of my face, and the electrons in my face is getting to you. So the electrons get excited, and they fall back down, and they release a photon. So the electrons go from the ground state to the excited state. They get there because they absorb a photon, and when they go back from the excited state to the ground state, they release the photon. And photon is just a quantum of light, an energy package of light, okay? And so different photons are going to have different package amounts, and they're going to give you different colors based upon those different package amounts, okay? So it falls back down, releases a photon, and again, they have different energies, and they're going to respond to the different colors based upon the different jumps. So we're going to show you a couple of those jumps here. Now, here's one jump. Now, notice I've got a piece of energy. Well, actually, not quite showing you the energy coming in. But let's say I had a big old piece of energy come in, and it hits that electron. It jumps up, and then it's going to fall back down once it's not excited anymore, and then it releases that photon of light. Same thing here. If I have an electron and some light comes in, it hits it, and then it jumps up, and then when it comes back down, which we're showing you there, it's going to release this photon of light. Now notice that I have two different colors there, okay? And that's intentional. The color here is red, the color here is orange. Red is a lower energy wavelength of light. Okay, it has less energy than blue, for instance, and it also has less energy than orange. Okay, Roy G. Biv. They go in that order for a particular reason. That's the order of the energy that they have. So violet light has a lot of energy, really small wavelengths, fast frequency. Okay, red light has a longer wavelength, and it's a slower frequency, and it has less energy. And so if the electrons are jumping bigger amounts, then when they fall back down, they're going to give off more energy light. Notice that the wavelengths are shorter here. If the electrons are jumping smaller amounts, then they're going to give off smaller amounts of energy, and so the light's going to be more in the red spectrum versus the orange spectrum. And so if I wanted to say, okay, well, what's it going to be if it's blue light or something? Well, that's got to be an even bigger jump, right? And so the jump size corresponds to the light color. So gains energy, moves to a high energy level, and then it loses energy to move to a lower energy level, and it gives off light as it does so. Now here are the original pieces of energy that Bohr noticed when he was studying the hydrogen atom. Now there's only some of them that we can see. We've got this Lyman series and this Paschen series, but the Balmer series is what we can actually see. And so when we talked about those colors of light that hydrogen gave off, well, these are the colors basically that we could see that hydrogen gave off. And notice how they correspond to the energy jumps. So if I go from the 6 energy level down to the 2nd energy level, I'm giving this violet light. Blue was from 5th to 2, okay? Green was from 4 to 2, and red was from 3 to 2. So we're getting these different amounts of energy when we have different jump levels, okay? These are the returning stages. All right, and again, they've measured the amount of energy in electron volts, and you can see some of these are in the infrared radiation series, okay, so they're less, and some of these are in the UV radiation series, so they're more energy when you go to UV, okay? So, again, how do atoms produce light? When the excited electrons move to a lower energy level, they release the energy in the form of light. They release the energy in the form of photons. So let's look at a modern model summary. Now, this model came by the work of a lot of scientists, people like Heisenberg and Pauli and de Broglie, and a lot of different scientists that kind of came up with this through a bunch of different, steps and a bunch of different collaborations, came up with this modern model. So, this isn't one scientist, but there's a lot of things that we want to see that are going to be quite different than what Bohr came up with, right? Location of an electron cannot be predicted precisely. It's kind of like the blades of a fan, and this is part of what Heisenberg came up with. And if you've ever heard of the Heisenberg uncertainty principle, kind of relates to this. You can imagine the blades of the fan that are spinning around. And if you were to look up at the blades of the fan and you were to blink your eyes, you know how you can kind of stare and blink and all of a sudden you kind of see them stop for a second? Well, that second that you see them stopped, you can like, oh, it almost looks like it's still for just a second, right? But by the time you are actually even able to say that, the blades of the fan aren't there anymore. It's kind of like that with the electron. The electron's not even there anymore. Once we figure out where it was, it's gone. Okay, so we can't predict precisely where it's going to be. The other thing is that the electrons move in all sorts of crazy ways. They do not move around like orbits, like planets orbiting the sun at all. Okay, we're going to show you some of the weird places that they inhabit. But they inhabit general locations pretty predictably. They can kind of say, oh, we have 90% probability of predicting certain locations. All right, so they act like waves. Remember I said they kind of vibrate with wave-like properties. That's what is very unique. De Broglie kind of helped us understand that. Electrons travel like bees around a beehive, okay? Now, again, this is one of those that, you know, they're zipping all around. They're not in any sort of regular pattern, so this is not at all what Bohr was saying, okay? We'll show you a picture of where their beehive is here in a second. Electrons exist in certain regions called orbitals. And again, 90% probability of finding an electron in an orbital. It's just a region of space. You see, we kind of have like this idea of electron clouds. It's kind of like this. If I were to take a picture of an electron, and then I take another picture, and another, and another, and I take up a whole bunch of pictures, thousands of pictures of where the electron is. And it's just all over the place. By the time I superimpose all those pictures on top of each other, it kind of looks like a cloud. Okay, it's like, oh, that electron is kind of in this region. And that's kind of what they do. There are 4 different orbitals, and they have different shapes. There's S, P, D, and F. Okay, we're going to show you this on the next slide. Crazy shapes, some of them. S is pretty simple, looks like a sphere. P is not bad, looks like dumbbells. D and F, woo, they're getting a little crazy, all right? So if you have an S orbital, I can have 2 electrons in that space, and they look like spheres. The first energy level is smaller than the second energy level, and that's going to be the case for all of these. If you have a particular type of orbital in a particular energy level, you're going to have the same orbital in the next energy level. It's just going to be bigger. So I go from 1s to 2s, but if I go from my p's and I go up to 3p, they're a little bit bigger, right? So there's an axis where they have 3 different ways that the electrons could be. So it kind of looks like a little dumbbell. But I could have 2 electrons in this little orbital here, and I could have another 2 electrons in that orbital. I could have another 2 electrons in that orbital. Now, we don't know where they are at any one point in time. They could be in the separate sides. They could be in the same side. We don't know. And then if we kind of superimpose those, we've got the 1s, okay, it's a little sphere inside here, and then the 2s, bigger sphere, and then the 2p's are all over the place. So if we superimpose them, we kind of get the idea of where the electrons are. They're all over the place. Okay, this is not at all like Bohr's model, a nice, easy, spinning. No, it does not work like that at all. Okay, the mathematics hold up for Bohr's model for hydrogen, but they don't hold up for anything else. And then we have d orbitals, and then we have f orbitals. Now, the d orbitals kind of look like clover leaves to me. They have 5 different orientations. So this has 3 orientations. The d orbital has 5 different orientations of various different types of clover leaf and other interesting shapes. The f orbitals, there's 7 different f orbitals, and they're all over the place, crazy, crazy shapes. But you can still predict there will be 2 electrons somewhere in that orbital. There will be 2 electrons somewhere in that orbital. Okay? We don't know where, but this is the region of space that they exist. And if we take a bunch of pictures of where those electrons are at any one point in time, eventually we come up with this interesting shape. So isn't that wild? So that's the modern model of the atom. Now remember, models change all the time. And it's not bad to continue using Bohr's model of the atom because it helps us understand energy levels a little easier. Can't see the energy levels quite as well here. So models are okay to use even if they're outdated because they can tell us something about a concept that helps us to relate a little bit better. So don't be offended if somebody's using Bohr's model of the atom. You're like, yeah, that's not the quantum model. That's not the modern model. No, but it can still tell us some good things. Okay, still give us good information. All right, so I said we'd wrap this all up, bring it back to fireworks. I just thought I'd show you a little picture of a firework, how it works. You got this main fuse. It's going to get in there. Of course, this is going to lift that firework up into the sky. And then once this thing lights up, it's got these little pellets inside that have various different types of elements in them, right? Different compounds that are made up of different types of elements that will have different colors, different characteristic fingerprints. So if you wanted to have some green, you might have some copper in there. If you wanted to have some orange, you might have some calcium or some other different types of elements that are also orange. Sodium's a little bit orange. So you could have different types of chemicals inside these different stars, and when they blow up, then you're going to see those different colors, okay? So why do fireworks work? Well, because electrons like to absorb energy and jump up because they get excited. They absorb energy in the form of light, but they also absorb energy in the form of heat. And so when a firework goes off, that heat is enough to get those electrons excited and jump up. Normally in our class, we would do a lab where you could see different colors of light as it burns. And, you know, one of these times, maybe as you come in for this week, we'll give you an example of the fire colors that you can get when you burn some of these chemicals. It's pretty cool. So let's see what we learned today. Can we describe experimental evidence? Yeah, we talked about how light, okay, is given off with these different colors as we energize and electrify these things, and how we have fingerprints of atoms, right? Then that's going to tell us about Bohr's model, those different energy levels. And then we can now tell you what valence electrons are. Those are the outermost energy level electrons, and they have to do with reactivity. And then do we have evidence to help describe the modern model of the atom? Yeah, we do. Experimental evidence, remember, a couple things. We didn't go into a lot of detail, but Bohr was, you know, the main thing we talked about. But there are also other, you know, pieces of evidence like de Broglie, you know, was able to find out that electrons behave like waves. Lots of others that I'm not too worried about, but basically we focused on Bohr. The experimental evidence of Bohr that the electrons are no longer orbiting in orbits like planets, but they are kind of going to jump from one level to the next, right? So Bohr thought they were in planets, but he at least got the idea figured out that they jumped from one level to the next. And then it wasn't until you got to some of those other scientists that we didn't really get into where they found out that they didn't go in circles. But that's okay. You don't have to know those other ones. Just be focused on Bohr and his connection to the modern model. All right. So I hope you enjoyed it. Electrons are a lot of fun. Light is a lot of fun. And the connection between the two is a ton of fun. Hope you like this lecture. I hope you like learning about this stuff. I enjoy teaching it. And if you have any questions on it, please ask. There's so much more that I could teach you, and you'll learn a lot more in chemistry and physics too. All right. Have a good day. God bless you. Be kind to each other.